Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the mystery of light, not just what it is, but how it moves, and more curiously, why it stops, or rather, why it never goes faster than a certain pace. We're going to follow light as it races through space, whispering its secrets to gravity, to time, and to the very shape of the universe itself. We'll ask what it means for something to have a speed limit, not on a road, but in the vacuum between galaxies, and why that limit is precisely what holds everything together. Plungy, before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights. Maybe turn on a fan for a soft background hum. Let your thoughts stretch a little. Let your body settle. And let's begin our journey with a simple question. Isn't light go faster? That might sound like a silly thing to ask. Light is fast, blisteringly, impossibly fast. It zips around at 299,792 kilometers per second, which is nearly 186,000 miles every tick of the second hand. That's fast enough to circle the Earth more than 7 times in a single second. If you could travel that quickly, you'd reach the moon in just over a second. You'd get to the sun in a little over 8 minutes, and if you wanted to leave the solar system entirely, light could do it in hours, something no human has ever even come close to, breached. For something so unimaginably swift, light has a limit. It never speeds up, not even a little. Whether it's coming from a flashlight in your hand or a supernova 10 billion light years away, it always moves at the same speed. Always. Without exception. And that is strange. Perpetual, because most things don't behave that way. If you throw a baseball while riding a train, it goes faster. If you run on a moving walkway at the airport, your motion adds to the walkway's speed. But not light. If you shine a flashlight while flying at near light speed, the beam still moves away from you at exactly the speed of light. No faster. Not even a little. Blinked. It's almost as if the universe is telling light, you can go this fast, but no faster. And everything else, space, time, gravity, even causality itself, must obey that rule. But where did that rule come from? Why this particular number? And what does it mean for how the universe behaves? Tonight, we'll explore those questions gently. We'll look at what light is, how we came to understand its speed, and why it's woven so deeply into the laws of physics. We'll visit the minds of the scientists who wrestled with these puzzles. We'll imagine ourselves riding beams of light, slipping through space-time, and wondering what lies just beyond the cosmic speed limit. But we'll do it slowly, thoughtfully, softly. Bisexual. Because understanding something as vast and brilliant as light doesn't need to be loud. It can be like a whisper through a quiet room, or the glow of a street lamp outside your window at night. Gentle, patient, and illuminating in its own time. Kang to breath. Let your shoulders drop just a little more. And let's follow the light, together. Let's stay with this stillness for a moment. If you imagine yourself lying on the floor of a quiet room, lights off, ceiling above you, what would it feel like to float? Not upward or downward, but across something bigger than space. Across time. That's what light is doing, always. It isn't just moving, it's keeping time for the entire universe. You see, light doesn't just travel fast, it defines what we mean by speed at all. In fact, in modern physics, the speed of light in a vacuum isn't just a measurement, it's a fundamental constant of nature. One that doesn't depend on who's watching or how fast they're moving. We don't simply observe the speed of light, we build the entire framework of the universe around it. That number, 299,792,458 meters per second, is so important it's literally written into the very definition of the meter. Scientists used to define a meter by a metal rod in Paris, Now we define it as the distance light travels in a certain fraction of a second. The second itself is tied to the vibrations of cesium atoms, so time and space are now pegged to light's behavior. We've built our ruler and our clock around something that never wavers. Why? Because light is dependable. It doesn't slow down in a vacuum. It doesn't speed up if you chase it. It doesn't care how you move. If you're running toward a light beam or away from it, it's still coming at you at exactly the same speed. It was this unshakable constancy that puzzled scientists in the late 19th and early 20th centuries. And no one found it more strange or more beautiful than a young Albert Einstein. In fact, the realization that light speed is the same for everyone, no matter how they move, led him to a radical conclusion: that time itself must be flexible. Disproportionate. Disposed speed remain constant, space and time must adjust. Your clocks tick slower when you move faster, your rulers shrink, events rearrange themselves depending on your motion. The universe, it turns out, is not a rigid grid. It bends to protect the speed of light. That's astonishing, and just a little poetic. The fastest thing in the universe never changes speed. Instead, everything else changes to accommodate it. That's not just physics, it feels a little like humility built into the bones of reality. Why does light have a speed limit? We're really asking, why is the universe built around that limit? And that's what we'll quietly uncover tonight. But we'll explore light not just as a wave or a particle, but as a boundary, as a messenger, as a quiet architect of what is possible. And as we walk through the ideas that changed our understanding of time, motion, and space, we'll keep circling back to that one constant, light, and its quiet refusal to go any faster. This refusal shapes everything. It's billions of years ago. It's why the past, present, and future aren't the same for everyone, and it's why we'll never know what lies beyond the edge of the observable universe. Not because of a wall, but because light hasn't reached us yet. So, wherever you are, in bed, on a couch, or floating in your own pocket of quiet, know that light is still moving, right now, from stars, from phones, from the past. And even though it's the fastest thing we know, it takes its time. Patient, precise, and always just enough. Let's begin. Let's sit with light for a moment, quietly. You've seen it every day of your life. You've watched it pour through windows in the early morning, flicker from lamps when the power comes on, sparkle off rippling water, and glint from the screen you're looking at now. But what is it? Light feels like a presence, doesn't it? But you can't hold it. You can't scoop it up in a jar. It touches everything, yet remains untouchable. It seems to behave more like a whisper than a thing. And for centuries, scientists struggled to pin it down. At first, people thought of light as tiny particles, minuscule bullets travelling from your candle or the sun. Isaac Newton supported this idea. It made intuitive sense. Light casts shadows, bounces off mirrors, travels in straight lines. That sounds like a particle, doesn't it? Long after, experiments started to hint at something stranger. Imagine you're standing beside a pond. You toss a stone into it, and ripples spread outward in circular waves. Now imagine you have two stones, and you toss them both. Their ripples interfere, sometimes cancelling, sometimes amplifying each other. This is exactly what light does too. Thomas Young demonstrated this in 1801 with a famous experiment, the double-slit experiment. He shone light through two narrow slits and observed an interference pattern, a series of light and dark bands on a screen. The light seemed to be acting like a wave, rippling and overlapping with itself. But wait, is it a wave or a particle? The also somehow? Light is made of photons, tiny packets of energy with no mass. They can act like particles, colliding with electrons and knocking them loose in what's called the photoelectric effect. But those same photons can interfere like waves, creating elegant patterns of dark and bright bands. It's not that light flips between being a wave or a particle. It just is something more fundamental, something we don't have perfect language for, something that behaves like both, depending on how we look at it. This idea, that light defies classical categories, led to some of the most profound breakthroughs in science. In 1905, Albert Einstein used the photoelectric effect to show that light comes in quantized packets. That paper would win him the Nobel Prize, not for relativity, but for helping to launch quantum mechanics. What is light, really? Prolonged simplest, it's a form of electromagnetic radiation. That means it's an oscillating electric field and a magnetic field, dancing together, creating each other as they go. One wiggles, the other responds. And this mutual dance doesn't need air or water or any medium at all. Light can travel through the perfect silence of a vacuum, and it doesn't slow down, at least not in empty space. That's part of what makes it so special. As you lie in bed or curl beneath your blanket, through your window, from streetlights, from distant stars, from the Big Bang itself, they travel for billions of years, never tiring, never needing a pause. They move at one speed, always. And this dance of waves and particles, of fields and energy, is what illuminates your book page, your room, your world. It's so common, and yet almost no one ever pauses to ask what it really is. You just did. And that's where our journey begins. If you ever find yourself in a quiet moment, maybe walking through a hallway with old wooden floors or waiting for water to boil, it's lovely to imagine that the universe, underneath all its noise, is held together by invisible symmetries. One such symmetry was uncovered not by chasing stars or building telescopes, but by scribbling equations on a page. His name was James Clerk Maxwell, a Scottish physicist with kind eyes and wild hair. He brought together electricity, magnetism, and a touch of poetry into 4 elegant equations. You don't need to know the equations themselves, though they are surprisingly beautiful. What matters is what they whispered to the world. Maxwell discovered that electric and magnetic fields aren't just forces that act at a distance. They can create each other. A changing electric field creates a magnetic field, and a changing magnetic field in turn creates an electric field. In this way, they can move through space, leapfrogging each other like a never-ending game. And here's the magic. When Maxwell worked through the math, he discovered that this self-sustaining wave, the oscillation of electric and magnetic fields, would naturally move at a specific speed. He calculated it. He ran the numbers, and the answer, to his astonishment, was the speed of light. Phantom was a turning point. It suggested that light itself is this electromagnetic wave. That light doesn't need a medium to travel through. It is the thing that moves. Like a whisper that carries its own air, a ripple that doesn't need water. At the time, this was revolutionary. People believed in the luminiferous ether, a mysterious substance that supposedly filled all of space and allowed light to travel. After all, how could a wave move without something to wave in? Sound needs air. Water waves need water. How could light ripple through emptiness? But Maxwell's equations didn't mention ether. They simply said, if you have the right conditions, an electric field and a magnetic field that feed each other, you get light, and you get a speed. Bracelets wasn't just any number. It came out to about 300,000 kilometers per second. It was in fact the same speed that experimentalists have been measuring for decades as the speed of light. So now, it wasn't just observed, it was predicted. That's when you know you're touching something deep. This revelation that light is an electromagnetic wave bound together electricity, magnetism, and optics into one unified theory. And the speed of light was no longer just a curious figure. It was a fundamental consequence of the structure of the physical world. And still, despite this elegance, something felt incomplete. It must have something measures something to something mere measures. Aniascals and a telesynths of manical telesynths. Right? But what if light didn't care about your speed at all? That's where Einstein would pick up the thread years later. But before we meet him, take a moment to appreciate Maxwell's gift. A set of equations that didn't just describe fields, they predicted the very motion of light, hidden in the silence of math, waiting patiently to be read. And that, quietly, changed everything. Imagine you're floating in space. No sound, no air, no walls, no floor, just you suspended in the black, with only your breath in your helmet and the hum of your own thoughts. Now imagine turning on a flashlight. In this perfect silence, in this emptiness between stars, light still shines. And it moves, at full speed. That's odd, isn't it? Because most things we know, most waves, need something to travel through. Sound, for example, is a wave in air. Without air, there's no sound. That's why explosions in space are silent. No matter how dramatic they look in movies, in reality, they'd be entirely mute. Water waves need water. Seismic waves need ground. But light? It doesn't need anything. The different-century physicists hit a wall of confusion. If light was a wave, it had to wave through something, right? That's why they imagined the luminiferous ether, an invisible, undetectable medium that filled all of space, giving light something to ripple through. But try as they might, they couldn't find it. Freeze's attempt came from two scientists, Albert Michelson and Edward Morley. They built a device, an interferometer, to detect the Earth's movement through this mysterious ether. Like feeling the wind while riding a bike, they expected to find a difference in light speed depending on the direction of motion, a sort of cosmic breeze. But when they ran the experiment, nothing changed. Pensions, no matter the direction, no matter the time of year, light speed stayed the same. It was as if the ether wasn't there at all. And this result, so frustrating at the time, would become one of the most important clues in physics. It whispered that maybe light didn't need a medium. Maybe the idea that waves must ripple through something was a limitation of our own expectations, not of nature itself. Maxwell's equations had already hinted at this. They described self-sustaining waves of electric and magnetic fields. No background substance required, just the fields themselves, dancing in tandem. So what is the vacuum of space? To us, it seems like nothing, but to light, it's enough. It's the perfect canvas. In fact, light moves fastest in a vacuum because there's nothing to get in its way. The moment it enters glass or water or atmosphere, it slows slightly, not because it's tired, but because it interacts with the material, bouncing from atom to atom, like a crowd slowing your walk down a hallway. But in true emptiness, it stretches its legs. It moves at the ultimate speed limit, effortless, unstoppable. And here's something even more beautiful. This speed, light's unchanging, unwavering pace, is not just about convenience. It defines the geometry of the universe. It's built into the way time and space respond to motion. Blindness light moves. It doesn't ask permission. It doesn't lean on a medium. It simply is. A self-contained whisper of motion, a wave without water, a message without a wire. The clue that Einstein would chase, wondering how something could remain so stubbornly constant, no matter how fast you ran after it. Picture a very simple clock. Not one with gears or ticking hands, but something more elegant, more fundamental. Imagine two mirrors, one above the other in a perfect vacuum, and between them, a single beam of light bouncing back and forth. Up, down, up, down, tick, tock. Each bounce marks a moment, each round trip a measure of time. This is the light clock, a thought experiment that physicists love for its simplicity, because in its silence, it reveals something profound. Let's say you're floating beside it, watching the light bounce. It moves in a straight line, regular, steady, predictable. Time, you might think, is unfolding exactly as it should. But now imagine someone flies past you, carrying an identical light clock. From your point of view, their clock is moving sideways, as well as ticking up and down. And so, From your perspective, the light inside it has to travel diagonally, zigzagging between the mirrors instead of going straight. This means the light has farther to go with each bounce. It takes longer to reach the top mirror and back again. But, and here's the beautiful part, the speed of light doesn't change. Remember that. It's constant. Always. Cipher. The light travels, gets longer, but the speed remains the same. Then something else must adjust. Time. From your viewpoint, their clock is ticking more slowly. This is not an illusion, not a trick of perspective. It's a real, measurable effect called time dilation. The faster someone moves relative to you, the slower their time appears to pass. Their seconds stretch out, their watch ticks more slowly, their light takes longer to bounce. And all of this, every part of it, is rooted in the constancy of the speed of light. You might wonder, how could a beam of light, bouncing between two mirrors, dictate the nature of time itself? But that's what makes this so astonishing. It tells us that time is not absolute, that clocks don't agree just because they're clocks. They depend on motion, on perspective, on how space and light interweave. And it all traces back to that single beam of light, refusing to change its pace. Einstein understood this deeply. In his 1905 paper on special relativity, he started with a simple postulate that the laws of physics are the same for all observers, and that the speed of light is constant in all frames of reference. From these quiet principles came an upheaval of everything we thought we knew, because if light always moves at the same speed, then time must bend to accommodate it. This is why astronauts on fast-moving ships age slightly slower than people on Earth, why GPS satellites need constant adjustments to stay in sync with ground-based clocks, and why light, with no mass beam, bouncing forever in empty space, measuring the pace of existence. Light doesn't just illuminate the room, it measures the moment. Close your eyes for a moment and imagine you're in a sailboat. The wind brushes against your face and you feel its direction. You adjust your sail, you can tell, without even looking, that you're moving, because you feel the breeze, because the air seems to shift as you pass through it. Now imagine the Earth, sailing through space. 19th century scientists believed that if light was a wave, it must ripple through something, just as sound ripples through air or ripples travel through water. So surely there had to be a medium in space for light to travel through. They called it the luminiferous ether. The ether, they imagined, filled all of space. It was weightless, invisible, undetectable, but absolutely everywhere. A cosmic stillness. The sea through which Earth moved. And just like the wind in your face on that sailboat, Earth's motion through the ether should have produced an ether wind, a measurable effect that could be detected. At least, that was the idea. In 1887, two physicists, Albert Michelson and Edward Morley, set out to find this wind. They built a clever instrument, the Michelson-Morley interferometer. It split a beam of light in two directions, one in line with the Earth's motion and one perpendicular to it. The idea was simple. If Earth was moving through the ether, then light travelling along the wind should take a different amount of time than light going across it. When the two beams came back together, any difference would show up as an interference pattern, a gentle shimmer like ripples colliding on a pond. But no shimmer came. Meliors from they tested it. Morning, night, summer, winter. No matter which way they turned the device, the speed of light appeared completely unchanged. No ether wind, no medium, just light, moving at the same speed in every direction. Impossible non-results in scientific history. And it left physicists puzzled. If there was no ether, how could light travel at all? And if there was, why couldn't we detect our motion through it? The answer wouldn't come right away. Some tried to patch the problem with elaborate fixes, like shortening rulers or slowing clocks in just the right way to make the ether undetectable. But it was Einstein, nearly 2 decades later, who proposed the boldest solution, flushing what if the ether simply doesn't exist. What if light's behavior doesn't depend on any background substance? What if its speed is the same for all observers, not because we're all moving through some silent sea, but because that's just the nature of light? This idea was radical. It meant letting go of the ether entirely. It meant trusting the constancy of light and accepting that space and time must bend around that truth. And that's what physics did. The luminiferous ether, once seen, never touched, never needed again. Instead, we were left with something more beautiful, a universe where light needs no medium. A beam that travels through perfect nothingness, carrying information, energy, and the memory of distant stars, all without a wave to ride on. Just light. Alone, and enough. Let's return to a simple word: constant. In most of daily life, constants are boring. A constant headache, a constant drizzle, a constant hum from the fridge at midnight. But in physics, constants are sacred. They're the quiet promises the universe makes to itself, the numbers that never change no matter what else does. Blink to speed of light is one of those promises. When we say that light speed is constant, we don't just mean it's always fast. We mean that no matter how fast you're moving, no matter what direction you're going, no matter where you are in the universe, light travels at the same speed relative to you. This is so counterintuitive it's hard to believe at first. Imagine you're in a car, tossing a ball forward. To someone standing still, the ball moves faster because it has the speed of the car plus your throw. That's how we expect things to behave. Velocities stack, they add. Light. Not with light from a moving car, and you'd expect the beam to go faster than usual. But it doesn't. The person outside the car and the person inside both measure the beam moving at exactly the same speed. 299,792,458 meters per second. Not a millimeter more, not a blink less. This constancy isn't just quirky, it's disruptive. It breaks our classical intuitions, and it forces a change in something we thought was unshakable: time. See, to preserve light's constant speed for all observers, something else must give. And that something is the flow of time itself. It means clocks tick differently depending on how fast you're moving. It means two people can disagree on whether two things happened at the same moment. It means there's no universal now. All of that just to let light keep its promise. The idea that time is flexible, that simultaneity is relative, that space and motion are interwoven, all of it rests on this single truth: light speed never changes, doesn't just shape abstract physics. It defines how we measure everything. Time, distance, energy, motion, they all tie back to the speed of light. In fact, we now define the meter based on how far light travels in a tiny fraction of a second. It's not that light obeys the speed limit. We made the speed limit into a ruler, and when we look out into space, we're seeing the effects of this limit everywhere. The light from the moon took a little over a second to reach you. From the sun, about 8 minutes. The stars you see overhead tonight, some of their light left before you were born. It's not just a speed, it's a delay, a reminder that what you see is never quite now, it's always then, a shimmer of memory carried across space at light's fixed pace. So when we say light is constant, we don't just mean it's fast, we mean it's faithful, unchanging, the one thread of certainty running through a universe that bends, flexes, stretches and evolves. Maya line drawn not in the sand, but in the fabric of reality itself. Let's imagine you're 15 years old again. You're walking home from school, not thinking about dinner or homework or who you might sit next to tomorrow. Instead, you're wondering something peculiar. What would it look like if you could catch up to a beam of light? This was the question that a teenage Albert Einstein carried in his mind like a lantern. He didn't have a lab, he didn't have equations. He just had a strange, stubborn thought that wouldn't leave him alone. If you could chase a light beam fast enough, if you could match its speed, would the light just freeze beside you? Would you see a frozen wave hovering still, like a ripple caught in crystal? Would time stop? Would the light even still be light? It was an innocent question, but it held a grenade. Because according to everything physicists thought they knew, light was a wave, and waves have to move. The frozen wave doesn't make sense, any more than a sound wave that stops sounding, or a ripple that doesn't ripple. Position sensed that something deeper was hiding behind this paradox. That maybe light wasn't the thing behaving strangely. Maybe it was our expectations that needed to bend. Chasing light wasn't like chasing a car or a train or a baseball. You couldn't catch it. No matter how fast you moved, no matter how much energy you had, light would still race away at the exact same speed. From every frame, from every perspective. It was as if light didn't care who was watching or how fast they were moving. That realization was the seed, the quiet revolution. Years later, Einstein would call this his thought experiment. But it's more than that. It's the moment when the classical view of motion, of space and time as fixed and absolute, began to crack. And out of that crack came a new kind of physics, one not built on certainty, but on constancy, not on fixed backgrounds, but on unshakable relationships. Light became the measuring stick, the reference point for everything. If light always moves the same, then motion itself must be relative. Time must be flexible. Space must stretch or shrink depending on how you move. The universe, it seemed, would twist itself into knots to protect light's unchanging pace. And this wasn't a flight of fancy. It was the beginning of special relativity. It's easy to forget that the most profound changes often start with a single question, asked at the right time with quiet persistence. What happens if I catch up to a beam of light? Blackmail would lead to the end of the ether, the collapse of absolute time, the unification of space and motion, and a new vision of the universe where nothing outruns the truth, not even the light itself. Let's pause for a moment and imagine the universe stripped down to its simplest rules. No clutter, no distractions, just two guiding principles like quiet stars to navigate by. Softly, with two postulates that seem almost gentle in their wording, but from them an entire new understanding of space and time would unfold. Blackmail is the principle of relativity. It says, the laws of physics are the same in all inertial frames of reference. Picture yourself sitting on a train that's gliding smoothly along the tracks. There's no bumping, no screeching, just motion so smooth that if you closed your eyes, you wouldn't even know you were moving. You toss a ball straight up, it comes back down to your hand just as it would if you were standing still. Is what an inertial frame means. A place where you are either at rest or moving at a constant speed in a straight line. And within that frame, the laws of physics behave exactly the same. Whether you're on a train or standing on the platform, gravity pulls, balls fall, and nothing in the room around you gives away your motion. Discharged Galileo would propose something similar centuries earlier, but Einstein took it a step further. The second postulate is what made the ground shake. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. Let that sink in. It doesn't matter whether the flashlight is moving, or you are, or both. You will always measure the light's speed as exactly the same, no matter what. Everything else in nature. If you throw a baseball while walking, the speed of the ball depends on your motion and its own, but not light. Light is defiant. It refuses to follow that rule. Its speed is not additive, it's constant. Subjected you accept these two postulates, something curious begins to happen. You can't keep space and time as they are. If light's speed stays the same for everyone, then time must stretch for those who move quickly, and space must contract. Even simultaneity, the idea that two events happen at the same time, falls apart. These are not added consequences. They're necessities. The only way to keep the two postulates true. Didn't come to these ideas by force. He didn't twist equations or search for loopholes. He simply took light at its word. He trusted that if light moves the same for everyone, then the rest of the universe would have to adjust around it. Blackmailably, it did. From these two quiet principles, special relativity was born. Not in a lab, but in thought, like a soft breath bending the pages of a physics book. The rules weren't broken, they were rearranged, and the light kept moving, just as it always had. Let's try something strange. Imagine you're standing in the exact middle of a train car. The train is moving smoothly along the tracks. Now imagine two lamps, one at the front of the train, one at the back. Both flash at exactly the same moment. From where you're standing, you see both flashes at once. Light from the front and back reaches you at the same time. So you conclude, they must have turned on at the same time. Prosecute someone standing on the train platform as the train speeds past. Fruit go. From their perspective, you and the train are moving forward, so when the lamps flash, you're already drifting toward the front of the train and away from the back. That means to the person on the platform, the light from the front lamp has a shorter distance to travel to reach you, while the light from the rear lamp has farther to go. And yet you saw them both at the same time. Flush means that to the platform observer, the flashes couldn't have happened simultaneously. For the light to reach you at the same time despite those different distances, the rear lamp must have flashed before the front one. Let that sink in. Watching the exact same event disagree on which light turned on first. Friendly, and here's the catch, neither is wrong. This is the heart of what Einstein called the relativity of simultaneity. The idea that whether two events happen at the same time depends on who's observing them and how fast they're moving. It's unsettling, liberating ideas in physics, because it challenges something we hold deep in our bones, the belief in a shared now, seizing about the present as if it's universal, as if somewhere there's a ticking master clock that keeps time for the cosmos, but there isn't. Now is not an absolute, it's a point of view. And when observers are in relative motion, their slices of time, what they consider happening now, do not align. Not mean time is an illusion. It means time is woven into space, and motion pulls at the threads. In Einstein's universe, there's no giant spotlight sweeping across the cosmos, illuminating what's happening right now. There are only local clocks, and what those clocks say depends on how you're moving through space. Like watching lightning from two different hills. One person sees the flash over the east ridge first, another sees the west. Their landscapes shape their perceptions. And in the world of relativity, motion shapes reality. Buffering, all of this stems again from light's unchanging speed. To preserve that constancy, we must let go of our shared now. We must allow time itself to stretch and shift between observers. What once felt firm becomes flexible. With that flexibility comes a new kind of beauty. A universe not ruled by one ticking rhythm, but a chorus of ticking clocks, each singing its own version of the present. Let's imagine a pair of twins. Identical in every way, same laugh, same freckle on the same cheek, but with very different travel plans. One twin stays home, working in a garden, watching the seasons pass. The other climbs into a spaceship, accelerates to near the speed of light, and disappears into the cosmos for what seems like just a few years. When the traveller finally returns, they expect a joyful reunion. But something strange has happened. Desperation, who stayed behind, has grown noticeably older. Wrinkled, grey, a lifetime has passed. While the spacefaring twin, still young, steps off the ship, hardly aged at all. This isn't science fiction, and it's real. The idea is simple, though its consequences feel anything but. The faster you move through space, the slower you move through time. This isn't a trick of perception, it's not just how things look. It's how time behaves for different observers. When someone moves near the speed of light, time stretches out for them. Seconds lengthen, processes slow, aging slows. And it's all rooted, once again, in light's unwavering speed. Let's revisit the light clock for a moment. Picture a beam of light bouncing between two mirrors. From a stationary observer's point of view, the light travels a straight path, tick-tock, up and down. But if the entire setup is moving sideways, say, on a spaceship, then the light must travel diagonally. Its path is longer. But since light can't go faster to make up for the extra distance, the only option is for time itself to stretch out. Laminae sticking slows, and because biological processes, from heartbeats to cell division, are governed by time, those slow down too. Everything does, not just the clock, but the person. Their entire life takes place more slowly from the perspective of someone staying still. This has been confirmed in real experiments. Muons, short-lived particles created high in Earth's atmosphere, should decay before reaching the ground, and yet many are detected at the surface. Why? Because from our point of view, their time runs more slowly as they travel at nearly light speed. They live longer, or rather, we see them live longer. They orbit Earth at high speeds, where time ticks just a little more slowly than on the ground. Engineers must account for this, or else your phone's navigation would drift. Meters then kilometers, off course every day. So, what feels like a philosophical idea is also practical. The universe adjusts, and we've learned to listen. Presumption it is more than just an equation. Forbidden reminder that motion changes how we age. That speed warps not just your path, but your very experience of being. That someone moving fast enough can skim across the top of decades, watching entire histories pass below them, like a bird flying low over rivers of time. From their perspective, nothing feels unusual. Their clock ticks normally. Their thoughts are smooth. It's only when they return, when they step out of their frame into someone else's, that the truth becomes clear. Time is not universal. It's personal, woven into your motion, quietly stretching or folding to keep light honest. Imagine a train rushing past you at nearly the speed of light. It's long, hundreds of meters, and sleek like a silver ribbon, slicing through the air with barely a whisper. Now, from where you're standing on the platform, watching this train streak by, you notice something peculiar, conquered, shorter than it should. Not because it's far away, not because of perspective, but because it's moving so fast that its very length appears to shrink. This is length contraction, a natural consequence of special relativity and the quiet twin of time dilation. Just as time stretches when you move faster, space contracts in the direction of motion, but only from the viewpoint of someone watching the motion, not from within it. Folk passengers on the train, nothing feels different. They walk up and down the aisles, stretch their legs, look out the windows. To them, the train is its usual size, but to you, standing still, the whole thing looks compressed, like someone quietly folded a corner of space, administered a trick of the eye. It's not some blur caused by speed. It's a real, measurable effect. And it comes, once again, from the universe's loyalty to light. Balloons. The speed of light stays constant for all observers. To preserve this, space and time must cooperate. If time slows down for something moving fast, and light must cover the same ground at the same speed, then space itself must shorten along the direction of motion. It's as if the universe says, well, if you won't let light go faster, and you've already stretched time, then I'll just squeeze space. Disarm something moves, the more it shrinks, from the outside perspective. At everyday speeds, this effect is negligible. A car on a highway doesn't seem to contract because it's far too slow, but at relativistic speeds, when you start to approach the speed of light, length contraction becomes significant. Let's try another metaphor. Imagine you're standing still, holding a measuring stick. Now someone runs past you, holding the same kind of stick. If they're fast enough, their stick will appear shorter than yours, not just visually, but physically, from your frame of reference. But to them, your stick is the one that looks contracted. How can both be right? Dictatorship, there is no absolutity. There is no absolute ruler. No universal yardstick that everyone agrees on. Measurements of length, like time, depend on your motion. Space, like time, is flexible, and the faster you move, the more it flexes. The symmetry is strange, but essential. From your point of view, they shrink. From theirs, you do. And both observations are valid within their own frames. Interplay between shrinking space and stretching time is what makes special relativity feel so surreal. It's not just that clocks run differently. Rulers do too. The fabric of the universe isn't fixed. It adapts, precisely, without ever disturbing the speed of light. And as, strange as this feels, it all unfolds quietly, invisibly, every time something moves fast enough. Like time dilation, length contraction is not a distortion, it's a reconciliation, a gentle shift in the structure of space, keeping everything consistent. Like a type pass by, let your mind drift for a moment. What if it were moving faster? Much faster. You'd see it shrink, not because it's going away, but because space itself knows how to bend. Let's say you flip a light switch. A moment later, the lamp glows. It's such a small thing, a reflex, a blink, but behind it lies a quiet certainty we all take for granted. That what you do has consequences, that one event leads to another, that cause comes before effect. But in the relativistic universe, Einstein's universe, this chain of events is protected by something deeper than habit. It's protected by light. Sluggish. The speed of light isn't just the pace at which beams race through space. It's the speed limit of causality. Nothing, not a signal, not a force, not even a whisper of information, can travel faster than it. This isn't just a constraint, it's a safeguard. Because if something could travel faster than light, strange things would happen. Dangerous things. Imagine you could send a message faster than light, perhaps a cosmic telegram to a friend on a distant planet. To you, it feels instantaneous, but from their point of view, depending on their motion, it might look like the message arrived before you sent it. Now imagine they respond. Their reply too travels faster than light. From your perspective, it shows up before your original message was sent. Suddenly, you're getting answers before you ask questions. You're causing things to happen in the past. You've broken the sequence, the sacred order of cause and effect. Confusing. It's paradoxical. Minimized. You could go back in time and prevent yourself from sending the message at all. You could undo the very thing you already did. The logic unravels. Prometheus sees aren't just theoretical headaches, they're violations of causality, the foundational structure of how events unfold in time. And to preserve causality, the universe seems to enforce a strict rule. Nothing outruns light. To understand this visually, physicists use something called a light cone. Flushing you're a point in space-time, say, flipping that light switch. From that point, light spreads out in all directions, forming a cone of influence. Everything inside the cone is what you can affect. Everything outside, it's unreachable, for now. If you want to send a message, share a signal, or kick a soccer ball across the stars, you must stay within that cone. Outside the cone are other, neither in your future nor your past, simply disconnected. Because to reach them, you'd have to go faster than light, and that's not allowed. Not just by physics, but by logic itself. Causality is sacred, and light is its guardian. Discriminate. Light speed becomes more than just a number. It becomes the boundary between what can be changed and what cannot, between what has happened, what can happen, and what is forever out of reach. So when you flip a switch or press a key or speak a word into the air, you're not just causing an effect, you're sending ripples inside a cone. Ripples that will never spill over the edge. That can never outrun their moment. Because light is not just fast. It's just. Some equations are so famous, they seem to hum when you say them aloud. E equals mc squared. Just 3 letters, 1 equal sign and a superscript. But it carries the weight of stars, of energy released in fire and fusion, of transformations both subtle and staggering. Let's unpack it gently. E stands for energy, the capacity to do work, to lift, to heat, to shine. M is mass, the amount of stuff in an object, what you feel when you lift a stone or push a bicycle uphill. Shields is the speed of light squared, a big number, roughly 90 billion kilometers squared per second squared. Enormous. Energy equals mass multiplied by the square of the speed of light. That's what Einstein showed, that mass and energy are 2 forms of the same thing, different expressions of a single, deeper reality, like water and steam, or ice and rain, identical in substance, just transformed in state. And the speed of light? It's not just a constant. In this equation, it's the conversion rate between matter and energy, the bridge. It means even a tiny amount of mass holds a vast amount of energy, because when you multiply by c squared, even a pebble contains enough energy to power a city. If only you could unlock it. And sometimes, we do. In nuclear reactions, a small amount of mass is converted directly into energy. That's what powers the sun, fusion in its core. Hydrogen atoms fusing into helium, losing a bit of mass and releasing light and heat. That warm beam on your face at sunrise, it's mass turned to radiance. Expelled, it's also the principle behind nuclear power and nuclear weapons. The most concentrated release of energy humans have ever harnessed came from applying this quiet little formula. When uranium atoms split or fuse, mass disappears. Not a lot, just a whisper. and that whisper becomes a roar. But let's zoom out. Quarantine equals mc squared isn't just about bombs or stars, it's about connection. It tells us that mass isn't a stubborn lump of matter, it's potential. Every atom, every grain of sand, every breath you take is energy waiting to be rearranged. And that energy isn't abstract. It shines, it moves, it builds and breaks and rebuilds again. Einstein's equation also means that energy has mass. If you could bottle pure energy, light say, or heat, it would have weight. Not metaphorically, but physically. Energy and mass are bound together like melody and rhythm, distinct but inseparable. And of course, at the center of the equation is c, the speed of light. Its square gives the equation its scale. It reminds us that transformations between mass and energy aren't gentle, they're immense. Because light moves fast, but squared, it becomes a multiplier of awe. So next time you see sunlight on a sidewalk, or the quiet red glow of a heater in winter, remember, you're watching mass become energy, matter becoming movement. You're seeing Einstein's little equation come to life, humming to itself. Imagine you're aboard a spaceship. Not just any spaceship, but one designed to move faster and faster, closer and closer to the speed of light. You accelerate gently at first, feeling only a soft pressure as the engines push you forward. Outside your window, stars begin to stretch. Not in reality, of course, but in appearance. The universe starts to behave strangely. Just for you, feels normal. Your heart beats, your thoughts arrive in order. You sip from a cup of tea, and it still steams. But something odd is happening to the world beyond. Clocks on Earth, as seen from your fast-moving frame, appear to tick more slowly. Distances seem to shrink. The cosmos compresses. The faster you go, the more dramatic the effect becomes. This is what happens when you approach the speed of light. But here's the catch. No matter how much you accelerate, no matter how powerful your engines become, you can never quite reach it. There's a barrier, not physical like a wall, but mathematical. A soft but immovable boundary built into the structure of the universe. Let's look at why. As you accelerate, your kinetic energy increases. You're feeding energy into your motion. In classical mechanics, this would mean your speed keeps increasing linearly. But in special relativity, something subtler happens. The more energy you put in, the more your mass resists that motion. Not your rest mass, the kind you'd have standing still, but your relativistic mass, your resistance to acceleration. As you approach light speed, this effective mass increases. It's as though you're becoming heavier in the direction you're trying to move. Push harder, and the resistance only grows. Feed in more energy, and instead of going faster, time dilates. Space contracts. Your mass grows. But your speed asymptotically nears a ceiling. C, the speed of light, chasing a shadow that always stays one step ahead. You get close, closer than close, but never touch it. If you plotted this on a graph, your speed would form a curve that rises sharply, almost reaching the top, but never quite arrives. It flattens, forever just below the line. This isn't just frustrating, it's fundamental. Because at the speed of light, something profound happens. From a photon's perspective, if such a perspective were even possible, time stops. Distances vanish. A photon emitted from a star and absorbed by your eye travels across the galaxy in zero time from its own frame. That's part of why photons don't experience time. They're born and they arrive in a single, timeless moment. But for you, with mass, this is forbidden. Line back it would require infinite energy. And infinite energy doesn't exist, not in engines, not in stars, not even in theory. So the speed of light becomes more than a number. It's a boundary woven into existence, like a dream. Time slows, space shortens, motion becomes resistance itself. But you never quite arrive, of light's domain, and learn something just by getting close. Let's revisit your spaceship. You've been accelerating for years, quietly slipping closer and closer to the speed of light. Time outside your ship moves faster, distances warp, and your mass, your resistance to further acceleration, climbs. But still there's a question echoing in the back of your mind. Why, exactly, can't you go faster than light? After all, we've made machines go faster than sound. We've broken records before. Why not this one? On to the mathematics of motion. Let's start with momentum. In classical physics, momentum is just mass times velocity. But in Einstein's world, momentum includes a factor that grows dramatically as you approach light speed, a gamma factor, a mathematical stretch that increases without bound as you near the speed of light. This factor is tiny at low speeds, barely noticeable in everyday life, but as you go faster, it rises, slowly at first, then quickly, then explosively, and at the speed of light itself, it becomes infinite. This means the energy you'd need to reach light speed is also infinite. Camouflage how powerful your engines, how vast your fuel reserves, you'll always fall short. You can get close, you can make the world around you bend, flex, ripple, but to go faster would require an amount of energy the universe simply doesn't possess. If you could exceed the speed of light, you'd do more than break a record. You'd shatter the structure of causality. Remember those light cones? They're not just illustrations. They're the architecture of what can influence what. Cross that boundary, step outside the cone, and you risk flipping the order of cause and effect. Alphabetical in some frames of reference, your arrival might precede your departure. You might reach your destination before you ever leave. You could, in principle, send signals into your own past. The logic of reality would fracture. That's why physicists don't just say we can't go faster than light. They say mass cannot reach or exceed light speed without breaking the rules of space-time itself. Blackjack can. Plausible? Because light has no rest mass. A photon isn't something you can weigh. It's pure energy, moving at the only speed it can move. It was never at rest. It doesn't accelerate. It simply exists at light speed, from the moment it's born to the moment it's absorbed. Alibaba, on the other hand, anchors you. It tethers you to the structure of space and time. It gives you inertia, a resistance to change. That resistance increases with speed, and eventually it becomes overwhelming. So the speed of light isn't just a number we observe, it's a limit written into the geometry of the universe. A horizon we can approach but never cross. A silent barrier that says this far and no farther. And perhaps that's why it matters so much. Not just because it's fast, but because it draws the line between the possible and the paradoxical, between what can happen and what would unravel everything. Let's sit with a quiet idea. The universe, so vast, so chaotic, so filled with mystery, is also remarkably obedient. Stars burn, planets spin, and atoms cling together not through whim or randomness but through rules, patterns, boundaries, the kind of quiet discipline that turns chaos into elegance. And light is one of those rules, or more precisely its speed is. When Einstein built his theory of special relativity, he didn't invent something wild. He simply noticed a stillness in the way light behaved, that no matter how fast you moved or how carefully you watched, light refused to change its speed. It's this refusal, this constant, that forced everything else to bend. Time stretched, distances contracted, simultaneity crumbled, but light stayed steady. From that still point, the rest of physics reshaped itself, not like a demolition but like a dance, space and time adjusting their steps to stay in harmony with light's unyielding rhythm. It's tempting to think of this as a limitation, a cosmic no. You can't go faster than light, you can't send messages into the past, you can't escape time's curve. But what if it's not a barrier? Pilgrimage? What if it's a foundation? Redeemed, after all, aren't just boundaries, they're structure. They're the reason bridges hold, stories flow, and music makes sense. Without tempo, there's no melody. Without grammar, no meaning. Without constants, the world would drift. Light's speed isn't a cage, it's a framework. Cause of it we can measure, compare, predict. We can build technologies that whisper with satellites, navigate with precision, and even detect ripples in space-time. It's what lets us understand the past, not just our personal memories, but the history of stars. When we look up at the night sky, every point of light is a message, a story that began long ago, travelling across millions or billions of years, reaching us now, only because light keeps its pace. Blackmail of that pace, we've learned to listen. Flushing killed clocks that tick with atoms, telescopes that peer into the earliest moments of time, theories that connect motion, mass and meaning, all anchored to that simple speed. So when we say light moves at 299,792,458 meters per second, we're not just reciting a fact, simply we're whispering the tempo of the cosmos. Under mind that doesn't waver, a speed that gives time its meaning, a constant that lets reality unfold smoothly, gently, predictably, moment by moment, a world built not on chaos, but on quiet agreements. And light is the one the universe never breaks. Let's imagine you're standing in a perfectly still moment. You're in a quiet field, no wind, no sound, just you and a single match in your hand. You strike it, while a tiny flare of light blinks into the air, and instantly, the darkness begins to change. The light doesn't just radiate outward in space, it carves a shape into time itself. The idea of a light cone begins. It's not a cone in the ordinary sense, no ice cream, no traffic markers, but a shape that maps out where light can go after something happens, and where light could have come from before it. Picture it like this. From the moment your match sparks, light spreads outward in every direction at the speed of light, not just horizontally, but vertically, forward, backward, and sideways. If you plotted this in space-time, with space on the horizontal axes and time on the vertical, you'd get a cone, stretching upward into the future. Your future light cone. It contains all the places and events that your light could ever reach. Every planet, every particle, every friend across the galaxy. If your light can get to them, they're inside the cone. Anything outside that cone, it's still in the dark. You can't reach it. Not because you're too slow, but because even light hasn't had time to get there yet. Now flip the cone downwards. That's your past light cone, the set of all places that could have affected you at that moment. Every photon, every voice, every starburst whose light has arrived just in time to touch your eyes. Together, the past and future cones define what's causally connected to you, what can influence you, and what you can influence. Inside the cones, causality lives. Outside the cones, unreachable realms, separated not by distance, but by time and limitation. It's a strange thought, isn't it? There are parts of the universe that for all practical purposes might as well not exist for you, because their light hasn't arrived. Their stories haven't yet reached your chapter. It's physics. If something happens outside your light cone, say a supernova exploding in a galaxy 20 billion light years away, it doesn't matter how dramatic it is. Its light won't reach you. You'll never feel its gravity. It's not part of your now. Maybe it will be, billions of years from now, or maybe never, if the universe expands too quickly. This structure, these cones, are the scaffolding of space-time. They define the difference between before, after, and elsewhere. They protect cause and effect, and they remind us that even in a universe without walls or borders, there are still boundaries. They're just made of light. Flaming each person, each star, each moment, as the tip of their own cone, light spreading forward, receiving echoes from the past. Overlapping, intersecting, or drifting apart. Sometimes the cones touch, sometimes they never will. And all of this happens quietly. With every step you take, your cone moves. With every blink, it reshapes. Your influence ripples out at light speed. Not faster, not slower, just enough. Let's imagine you're holding a marble at the edge of a soft trampoline. You place the marble near the centre, where a heavy ball already rests, pulling the fabric downward. The marble rolls not in a straight line, but in a graceful curve around the dip, spiralling inward. You didn't push it. The surface itself, bent and stretched, is what guides its path and playful. is the simplest way to picture general relativity. Einstein's insight wasn't just that time and space adjust themselves for the sake of light's speed. It was that mass and energy bend the very fabric of space-time, and light, ever obedient, follows the contours of that bend. The straight lines of Newton's universe, the rigid gridwork of up, down, left and right, are gone. In their place are geodesics, the straightest possible paths through curved space-time. Imagine stretching a string tight around a globe. That string, hugging the surface, doesn't feel curved to someone walking along it. It's the shortest, truest path between 2 points on the sphere. That's what light does. It follows geodesics. Not straight in our everyday sense, but as straight as possible in a world that curves. So when starlight passes near a massive object, a star, a planet or a galaxy, it bends. Not because the light is being pulled like a ball on a string, but because it's simply following the space-time path available to it. Camouflage. Light obeys. Demolished. Its orbits work too. Planets don't circle the sun because they're being tugged by invisible hands. They're falling freely along curved paths in warped space-time. The sun doesn't pull Earth toward it. It reshapes the stage beneath Earth's feet, freezes in turn makes its own little dimple. So do you, as you sit here now. Every atom contributes. Every spark of energy bends the world, however slightly. The genius of general relativity is that it replaced the force of gravity with the shape of the universe. No longer something acting at a distance, but a change in geometry itself. Even time curves, passionately to a massive object, like a planet, or even more dramatically, a black hole. Time moves more slowly. This is gravitational time dilation, another form of light's influence, guiding not just the flow of objects, but the flow of seconds. GPS satellites account for this every day. Their clocks tick slightly differently than ours on Earth's surface, not because they're malfunctioning, but because they're higher in the gravitational landscape, closer to the top of the trampoline. It's subtle, but it matters. And again, at the centre of it all, is light. Bigotry defines the shape. It traces the bends. It tells matter how to move, and is in turn guided by what matter becomes. When you see the night sky shimmer, when you trace the arch of the Milky Way, you're watching the light of distant stars bending around space that itself is not flat. Enlightenment doesn't demand a ruler or a grid. It uses light, quietly weaving geometry into every step you take. Let's follow light to the edge of the knowable. Out there, beyond stars in silence, is something so strange, so quiet it hardly seems real. Not a solid thing, not a glowing thing, just a boundary. A place where light itself gives up. This is the event horizon of a black hole. To understand it, imagine standing at the bottom of a deep well. If you toss a ball straight up, it takes energy to fight gravity. The deeper the well, the more energy you need. If the well were deep enough, no matter how hard you threw, the ball would never escape, not even if you launched it at the speed of light. Blackmail that the well isn't carved into rock but into space-time. Black hole is a region where space-time is curved so intensely that the escape velocity exceeds the speed of light. It's not that light is slowed, it's that light cannot leave. It bends inward, spirals, sinks, is the edge, that event horizon. There is no turning back. All its speed and grace cannot escape. The moment it tries, it finds that the space ahead leads further inward. Like walking downhill forever. Every direction becomes down, every future path ends in the center. Outside, the horizon looks like a surface, a shell. But it's not a thing you can touch, it's just a location, a boundary in space-time where light's ability to reach the rest of the universe comes to an end. What happens beyond there to say? From our perspective, time slows down near the edge. A falling astronaut, to us, would appear to freeze, hanging at the brink forever. But for them, time feels normal. They fall, they pass the horizon without noticing anything strange, and once inside, the pull only grows stronger. Roofing at the center waits a singularity, a point where all the math breaks down, not because it's infinite in some poetic way, but because our current understanding simply can't describe it. Gravity and quantum mechanics begin to argue, and we don't yet know how to resolve their quarrel. With the center, we know the horizon is real. We've heard its echo, submerged through light but through gravitational waves, ripples in space-time created when black holes merge. The LIGO observatory detected them, like feeling the tremor of a distant bell we'll never see. And sometimes light does help, not from inside but from just outside. Submerged, spiraling toward the event horizon gets hot, furious, it shines. And when we look closely, we can see the silhouette of a black hole. the shadow it casts against the glowing chaos around it. The famous image from the Event Horizon Telescope, the dark circle rimmed by a halo of light, is not the black hole itself, but the boundary where light stops playing messenger. There is also a new need in that. For resonance in resulting universe turns inward, and stories no longer leave. It's strange to think that light shows us the limit of sight, practitioneth what it reveals, but through what it can't escape. That even in the deepest parts of space, the story of light continues, not in speed, but in silence. A reminder that even the fastest traveller has its edge, and beyond that edge there may be more, but not for us, and not now. Imagine walking past a puddle after a storm. The surface is still, smooth like glass, but when you look down, the world looks wrong. Trees bend, a street lamp stretches, the clouds shift in strange liquid ways. It's a perfect example of a gentle distortion, light taking a longer, stranger path to reach your eyes. Now replace the puddle with a galaxy cluster, and the street lamp with a galaxy far behind it. This is gravitational lensing, a cosmic mirage. It happens when light from a distant object bends around a massive one on its way to us, not because it wants to curve, but because the space it's moving through has been bent by gravity. The lens isn't a piece of glass, it's mass itself, space-time dipped inward by enormous weight. Einstein predicted this. He said that light, though massless, still follows the curvature of space-time. So if space-time bends near something heavy, like a star or a galaxy, then light will bend too, just like a car following a curved road. In 1919, Arthur Eddington confirmed this during a solar eclipse. He measured starlight bending around the sun, stars appearing just slightly out of place because their light had taken a warped path. It was the first major observational test of general relativity, and it made headlines around the world. AGIC happens on the grandest scales. When light from galaxies billions of light years away passes by galaxy clusters closer to us, we sometimes see rings, arcs, or multiple images of the same object. These are called Einstein rings and Einstein crosses, beautiful patterns formed when space itself acts like a lens. A single galaxy might appear as several, all stretched and smeared around the lensing mass. It's not duplication, it's distortion. The universe holding up a funhouse mirror. And just like those puddles, the distortions reveal something about the lens itself. By studying how the light is bent, we can infer the mass of the object doing the bending, even if we can't see it directly. This is one of the ways we discovered dark matter. The light told us there was more mass present than what we could observe. Invisible mass, pulling space into a dip. So gravitational lensing doesn't just show us what's behind, it shows us what's hidden in front. It's one of the universe's most generous tricks, using light not just to reveal but to map. Some of the most stunning deep space photos ever taken, like those from the Hubble Space Telescope, are filled with tiny streaks and warped halos. Many of them are lensing effects, and every one of those distortions is a quiet signature of gravity reshaping light's path. Something haunting about it. Coinbase could be galaxy could be seen twice, or stretched into a perfect ring, just because another galaxy sat in the way. Frosting, so persistent and straight, could be curved softly around a cosmic weight, like a river turning around a bend it cannot pass through. And yet, for all this twice, its drama, gravitational lensing, is silent. No flare, no sound, just a slow warping of space, and the patient light that follows can find distant galaxies into watery echoes. Picture someone walking away from you through fog, humming softly. At first their tune is clear, but as they move the sound stretches, lower, slower, like a record spinning down. That shift in pitch is the Doppler effect, and it's not just for sound, light does it too. When a star or galaxy moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, the light stretches toward the red. This is what we call redshift, a gentle elongation of light's wavelength, like pulling taffy or watching a wave flatten. Blackmail, but here's the strange part. When we observe distant galaxies, they're almost all redshifted. Not just a little, but a lot. And the farther away they are, the greater the shift. It's not that they're speeding away through space like cars on a highway. It's that space itself is expanding. Fabric of the cosmos is stretching, and as it does, it carries light along with it, stretching the wave as it travels. What begins as blue becomes yellow. What begins as visible may slip into infrared or beyond. It's not motion through space. It's motion of space. Discovery, made by Edwin Hubble in the 1920s, was one of the great turning points in modern cosmology. It showed that the universe isn't static, it's growing, and that growth is measured by light that has taken millions or billions of years to reach us, light stretched by a journey through expanding time. You can imagine it like you inflate it. The dots move apart, not because they're walking, but because the surface between them grows. That's what galaxies do in the cosmos. They're not flying away on rockets. The universe between them simply expands. Probation, and with each tick of that expansion, the light stretches further. The farther away something is, the older its light, and the more that light has had time to redshift. This lets us build a kind of cosmic ruler. The amount of redshift tells us how far the light has travelled, how long ago it began, and even softly, what the universe was like when it left. But redshift isn't just a measuring tool, it's a storyteller. It tells us the universe had a beginning, that once long ago, everything was closer together, hotter, denser. It hints at the Big Bang, not an explosion, but a swelling, a bloom of space and time from a state we still don't fully understand. It also helps us track the speed of expansion now, and in recent decades, we've learned that this expansion is accelerating, likely driven by something we've called dark energy, another whisper in the dark, measured by the way light fades redder than expected. Redshift turns the sky into a time machine. With every photon we catch, we're not just seeing stars, we're reading a stretched-out letter from the past. Imprisoned message carried across billions of years, slowed not by obstacles, but by the very breath of the universe itself. Fall back, and as you look up, know that the light in your eyes is older than anything you've ever touched. Because the sky is moving, and so is time. Close your eyes and imagine you're sitting at the edge of a vast lake on a windless night. You toss a pebble into the water, and ripples spread outward, gentle, patient circles growing wider with time. Now imagine you could watch those ripples for billions of years, tracing just how far they go before the dark swallows them. That's what light is doing in the universe. Each photon is like a ripple, leaving a source, stretching outward through space, travelling at the same speed it always has. And like ripples in a pond, their reach is finite, not because of obstacles, but because of time. This gives us something called the observable universe. It's not a bubble drawn around Earth like a snow globe, it's more like a horizon, the furthest distance from which light has had time to reach us since the beginning of the cosmos. Beyond that, things may exist, likely do, but their light simply hasn't arrived yet. Your viewpoint, this cosmic horizon, stretches roughly 46 billion light-years in every direction. Not because the universe is 46 billion years old, but because space has expanded while the light was on its way. Catching a firework from across a growing valley, by the time the sound reaches you, the space between has stretched. What you hear is older than the distance suggests. The light we see now left its source long ago, but travelled through a universe that changed beneath its feet. And the deeper we look, galaxies we see as tiny smudges may no longer exist in the form we see them. Some may have collided, evolved, or dimmed, but their light, their echo, still floats through the void, whispering what they once were. At the stars, you're not looking into space. You're looking into history. And this history is layered. Closer stars are younger in appearance, their light is fresher, but zoom out and the photons you detect come from further back in time, from epochs when galaxies were young, irregular, chaotic. Arrest still and you reach the first light, the cosmic microwave background, the glow of the newborn universe itself. We'll explore that next. Penetrated. But here's something quiet and wondrous to hold. You are always sitting at the centre of your own observable universe. So is every other observer, no matter where they are. The horizon wraps around each of us, not because we're special, but because light radiates outward evenly, everywhere. Swallowing. It's still travelling. Every second that passes, our horizon grows, new light arrives, new stories unfold, not from new galaxies, but from old ones, whose light has only now reached our eyes. Confiscated. A slow unveiling. A cosmic dusk gently brightening, photon by photon. And someday, far in the future, that unveiling will slow. Galaxies will redshift out of view. Light will grow thinner, dimmer, stretched too far to be seen. Not because it's stopped, but because we've drifted too far to catch it.
Yet. Chinook. Not tonight.
For now we are still held in light's gentle net, still reading stories written before we were born, still sitting quietly at the edge of a great lake, watching the ripples come home. Imagine waking up in a quiet room just before dawn. The windows are dark, but the air feels faintly different, like the world is holding its breath before the sun begins to rise. There's no noise, just a hush and a sense that something ancient is about to arrive. That's what the cosmic microwave background is like. Not a flash, not a crack of thunder, just a soft glow, a lingering warmth, a whisper from the very beginning. Need to travel back almost 13.8 billion years to a time when the universe was just a newborn, hot, dense and bright. But it wasn't a place where light could roam freely. Back then, space was like a foggy room filled with particles, protons, electrons, and photons constantly colliding, scattering, bouncing like restless children in a crowded hall. In this chaos, light couldn't travel far. It was trapped, absorbed and re-emitted endlessly. But then slowly things began to cool. The universe expanded and stretched. Particles calmed. And at around 380,000 years after the Big Bang, something remarkable happened. The fog lifted. Electrons joined with protons to form neutral atoms. Suddenly light was free, no longer blocked or scattered. For the first time, photons could fly uninterrupted across space. It's called recombination, and the light released during that era is what we now observe as the cosmic microwave background, or CMB. It's not visible like starlight. It's microwave radiation, cooler, quieter, stretched by billions of years of expansion. But it's everywhere. It fills the sky in all directions, and with the right instruments, you can see it. Like an ancient photograph of the universe as a baby. Newborn baby either. The CMB is mottled. It has tiny variations in temperature, just a few parts in 100,000. But those slight ripples were everything. They were the seeds of structure, the places where gravity would gather matter, where galaxies would form, where stars would one day burn. Alive because of those ripples. JFK, the first serious image of the CMB, came from the Kobe satellite in 1992, a gentle blur of uneven heat. Later missions like WMAP and Planck refined the picture, turning it into a cosmic fingerprint, policing. And in that fingerprint we find answers. The age of the universe, its composition, its geometry, whether it will expand forever. All of this is written in that quiet background hum. Light that's been travelling undisturbed since before any galaxy formed. It's astonishing to think. The most ancient light we've ever seen doesn't come from stars, but from a moment when the universe became transparent. The universe spoke and has never stopped. When you lie beneath the stars and feel the cold air, you're also being bathed, very faintly, by that light. It's too gentle to feel, too old. Silence. Know that it's not emptiness. It's memory. Imagine pointing a camera at the darkest, most seemingly empty patch of sky. A place with no bright stars, no obvious galaxies, no glow, just blackness. Now imagine holding that camera still, not for seconds or minutes, but for days. Letting it gather the faintest traces of light, patiently collecting photons like grains of ancient dust. That's what astronomers did with the Hubble Space Telescope, the Hubble Deep Field, and later the Ultra Deep Field, and even the Extreme Deep Field. These were quiet portraits of nothing that turned out to be everything. Images came back, they weren't empty. Each pinprick, each smudge of colour was not a star but a galaxy. Thousands upon thousands of them, each one containing billions of stars. Some so faint their light had taken over 13 billion years to arrive. These photons left their galaxies when the universe was young, when Earth didn't exist, when our sun wasn't born, when the Milky Way itself was still assembling. They travel through expanding space, dodging clouds, crossing silence, just to land in Hubble's lens. In that small patch of sky, just a sliver the size of a grain of sand held at arm's length, there were 10,000 galaxies. That's the power of deep field imaging. It doesn't just show us what's out there, it shows us what was. A time machine, not with gears or dials, but with exposure time. And now, with the James Webb Space Telescope, we're looking even deeper. Flooring its infrared eyes attuned to the oldest, reddest light. The light stretched so far by cosmic expansion that only these instruments can see it. And what it sees are galaxies in their infancy, clumpy, chaotic, raw, confiscated that have not yet settled into spirals, stabilised being born in the first cosmic nurseries. And as we look deeper, we begin to ask deeper questions. How did structure emerge from simplicity? When did the first stars ignite? How different was the early universe from the one we now call home? It's humbling to realise that every deep field image is built from light that never stopped travelling. Imagine a message written on paper, placed in a bottle, and sent adrift on an ocean that's been growing wider the entire time. That's what those photons are, bottle messages from the dawn of time. Here on a small blue planet, built a lens so patient, so precise, that it could catch them as they finally arrived. Grandparents, that moment, that silent arrival, is a reminder that light does not forget. It may stretch, protagonists, but it remembers. And it tells the story not in words but in the quiet scatter of galaxies painted across what we once thought was emptiness. Let's take a final pause and look at light not just as a messenger, but as an architect. Not with blueprints or bricks, not with hammers or noise, but with slow, persistent shaping. A quiet influence, a steady hand. When you imagine the forces that sculpt the universe, you might think of gravity first. And rightly so, gravity gathers. It pulls stars into galaxies, galaxies into clusters, and clusters into the grand web of the cosmos. But light shapes too. Submerged pull, it pushes. This may sound small, even polite, but it matters. The light from newborn stars exerts radiation pressure, pushing gently on the gas and dust around them. Over time, this pressure clears cavities in the clouds. It stirs the environment. It changes the path of future stars. Sometimes it prevents collapse, scattering material before it can clump into something new. Other times it's tessing gas into denser knots that go on to shine themselves. This balancing act of nurturing and limiting is called feedback, and it's essential to how galaxies evolve. Without it, galaxies might grow too fast, burning through their fuel in a flash of unchecked starbirth. With it, star formation becomes a dance, light and gravity pulling in opposite directions, sculpting each other's outcomes. And this influence scales upward. Wrongful and single stars to entire galaxies, light alters how gas moves, where stars appear, and how long they last. Massive stars, shining fiercely, often live fast and die young, exploding into supernovae, sending shockwaves and new radiation through their neighbourhoods. These bursts don't just announce the end of a life, they help seed the birth of others. Even the shape of galaxies can feel light's hand. The glowing disks of spirals, the halos of ellipticals, the dust lanes weaving through galactic arms, all carry signs of light interacting with matter. Light reveals form, but it also forms what it reveals, and sometimes light hides things. In dense galaxies, starlight gets trapped in clouds of dust, bouncing inside like fireflies in a jar. That hidden light, once discovered with infrared eyes, tells a more complete story, one we're only beginning to piece together with telescopes like Webb. We look at the sky and admire the elegance of a spiral or the puffed grandeur of an elliptical. We're seeing the outcome of light's silent guidance. Light doesn't just arrive, it shapes the path to its own arrival. Not quickly, not loudly, mailbox, but steadily. And over billions of years, this shaping becomes profound. Galaxies are not just collections of stars. They're stories of push and pull, of light whispering, "Not yet," or "Now is the time."
Choreography.
You were formed under that same light, and now you carry it forward, in your atoms, in your warmth, in the starlight caught behind your eyes.
Let's begin with something ordinary. You flick on a lamp. Light appears. You don't think about it, you just assume it's there, instantly.
The distance from bulb to book is so short, and the light so fast, that delay seems impossible. But what exactly is that light doing? And how do we know how fast it travels? For centuries, scientists believed that light must be instantaneous. After all, how could something so quick ever be measured? The stars appeared sharp, the sun lit the day without delay. Surely, they thought, light was infinite in speed. But one day, the sky told us otherwise. In the 1670s, a Danish astronomer named Ole Romer noticed something curious while observing Jupiter's moons. The moon Io, in particular, appeared to pass behind Jupiter slightly earlier or later than expected, depending on Earth's position in orbit. The difference? A matter of minutes. Gelatin. The variation came from light taking time to travel. When Earth was closer to Jupiter, Io's eclipse appeared sooner. When Earth was farther away, it was delayed. That meant light, like everything else, moved at a finite speed. It was the first time anyone had measured light's velocity, using space itself as the stopwatch. Later, in the 19th century, scientists refined the measurement. Hippolyte Fizeau and Léon Foucault used spinning mirrors and toothed wheels, bouncing beams across precise distances. These experiments brought light down to Earth, out of the stars and into the laboratory. Position, then something surprising happened. Instead of just trying to measure the speed of light, scientists began to define everything else in relation to it. Paved, today we no longer measure the speed of light. It's fixed. 299,792,458 meters per second. We've turned the idea inside out. Now, instead of measuring light, we use light to define the meter. Meter, the basic unit of distance in science, is no longer a physical rod in a volt. It's defined as the distance light travels in 299,792,458 second of a second. And that second? It's defined by the vibration of atoms. Specifically, the cesium-133 atom, ticking out time like a cosmic heartbeat. Time and space are now woven together, with light's speed as the loom. Finger's wish was more than just clever calibration, it was a quiet recognition of something deep, that light speed is not just a number, it's a constant of nature, one that underpins everything else. But what is light, really? It behaves like a wave, rippling through space with peaks and valleys. Other times it behaves like a particle, a tiny photon of energy, traveling in a straight line until it's absorbed. Neither model is wrong. Light is both, depending on how you look. And this dual nature allows us to count light. Photons can be detected one by one, like drops of rain falling on a rooftop. We've built devices so sensitive they can register a single photon arriving from across the universe. Each one a messenger, a traveller, and we measure its journey with clocks, mirrors, and silicon eyes. So when we say light moves at 299,299,458 meters per second, it's not just a statement of speed, it's a definition of distance, of time, of how we map the world. Light and mind things of seeding to reographics, the space we're going to be seed and start that health. It tells us what a second is. It tells us what a meter is. And in a way, it tells us where we are, simply by being itself. Let's talk about time. Not in the poetic sense, but in the precise, steady rhythm that lets machines talk, satellites navigate, and scientists listen to the cosmos. To measure something as fast as light, you need something even faster, or at least something perfectly consistent. That's where the atomic clock comes in. Before we peer inside one, think of a familiar ticking clock. It might mark seconds with a swinging pendulum, or a tiny quartz crystal vibrating with electricity. Useful, yes, but imperfect. These systems are subject to wear, heat, gravity, dozens of tiny influences that throw off their rhythm over time. Now imagine a clock that doesn't rely on mechanical parts at all. Instead, it keeps time with the natural vibrations of atoms, specifically the cesium-133 atom. Inside every cesium atom, electrons jump between energy levels in a regular, predictable pattern, and that jump happens 9,192,631,770 times per second. That's a second. Not because it was convenient, but because it was consistent, unshaken by weather or wear. Atomic clocks can lose or gain less than a second over millions of years. They don't tick with gears or springs, they resonate with the fundamental properties of the universe. This matter for light, because when you're measuring something that moves nearly 300,000 kilometers every second, even the tiniest hiccup in timing can throw off everything. Enter laser interferometric tools science has ever created. Imagine splitting a beam of light into two paths, sending them away, bouncing them off mirrors, and bringing them back together. If the paths were exactly the same length, the beams arrive in sync and reinforce each other. But if one path changes by even a fraction of a wavelength, the light waves interfere, sometimes adding together, sometimes cancelling out. Perpendicular behind devices like LIGO, the observatory that detected gravitational waves for the first time in 2015. Pescine uses laser beams fired down 4-kilometre-long tunnels, and it's so sensitive that it can detect changes in length smaller than a proton, about 1/10,000th the width of a nucleus. But such precision is only possible because the light used is predictable, and to keep that light honest, scientists sync their instruments with atomic clocks. Laser interferometers are like finely tuned ears, listening for ripples in space-time, but they need a steady metronome, a perfectly measured second, to detect when something's off. In essence, you're watching for light's rhythm to shift, just a whisper, just enough to say, something passed through here. Breastfeeding. Everyday lasers rely on light's steady beat. Laser rangefinders, for instance, send a pulse and measure how long it takes to bounce back. Multiply by the speed of light, divide by 2, and you've got a distance. But for that number to mean anything, your clock must know what a nanosecond is, or a picosecond, or smaller. Every beat must land exactly where it belongs. Without precision timing, our instruments blur, our signals drift, light's path becomes untrustworthy. Not because the universe has changed, but because we lost our rhythm. So we build clocks not just to mark time, but to hold stillness. We aim lasers not just to measure, but to harmonize with the fabric of space. And we listen, not with ears, but with carefully measured light. Because when you measure something that fast, you must first become very still. You reach into your pocket, tap your phone. A little blue dot appears on a map, showing where you are almost instantly. Maybe you're on a sidewalk, or in a forest, or driving down a winding road, and yet somehow that blue dot keeps up. It knows your speed, your direction, and your position within meters, sometimes even centimeters. That calm little dot is a system whispering with light, and behind that system is relativity. The Global Positioning System, or GPS, isn't just a network of satellites, it's a ballet of light speed timing and Einstein's equations in action. Here's how it works. Its Earth are at least 24 satellites, each carrying an atomic clock, each constantly broadcasting the time and its own precise position. Your phone listens to those signals. It picks up tiny pulses of light, radio waves travelling at light speed, and notes how long each one took to arrive. Tighten those arrival times, your phone triangulates your location. 3 satellites give you a rough position, 4 give you altitude. More than that, and things get even more accurate. There's the tricky part. Bannon the system only works if time is perfect. Stretch and time, according to Einstein, depends on motion and gravity. Bankers, the satellites are moving fast, about 14,000 kilometers per hour. They experience special relativity. Time on board ticks a little slower than it does down here on Earth. Their clocks run behind, by about 7 microseconds per day. But at the same time, the satellites are farther from Earth's surface, higher up in a weaker gravitational field, and according to general relativity, that means time ticks a little faster, about 45 microseconds per day faster. Plunge have 2 effects working in opposite directions, displaced because of speed, faster because of altitude. The result, satellite clocks run about 38 microseconds per day faster than clocks on the ground. That may sound like nothing, just 38 millionths of a second. Light travels almost 300 meters in 1 microsecond. If we didn't correct for those relativistic effects, GPS positions would drift by several kilometers per day. Your phone would think you were blocks away, then towns, then entire countries. Luckily, the corrections are baked in. GPS incorporate Einstein's time adjustments into every calculation. The atomic clocks are calibrated, the signals adjusted, the software prepared to listen across the relativistic divide. It's a quiet marvel, your location, your speed, your movement through a city, all made possible by the fact that we listen to how time bends. What once seemed like a thought experiment, a twin aging slower on a spaceship, or a clock ticking differently in orbit, now lives in your jeans pocket. So the next time you're navigating home, or looking up a hiking trail, or even just watching that little blue dot spin in circles in a parking lot, remember, you're holding relativity.
You're listening to satellites as they hum in orbit, whispering their timestamps at the speed of light, and you're trusting that those whispers take just the right amount of time to reach you. Not too fast, too slow. But exactly as light where gravity and motion bend every beat of the clock. Imagine calling someone who lives far away, not across town or in another country, but on Mars. You ask a question, and then silence. Not because they're ignoring you, but because the message is still travelling. Through empty space, across millions of kilometres, riding on a wave of light that moves as fast as anything can move, yet still takes minutes to arrive. This is the delay of distance, and it's not a glitch, it's built into the universe itself. Even though light travels at nearly 300,000 kilometres per second, the cosmos is just too vast for instant anything. Space doesn't care how fast you want to talk, it has its own scale, and light must obey it. Let's bring it down to Earth first. The moon is just over 384,000 kilometres away. That means a radio signal travelling at light speed takes about 1.3 seconds to get there. Not too bad. When NASA communicates with astronauts orbiting the moon, there's a noticeable pause. Questions hang in the air. Answers arrive just late enough to feel distant, unthinkable. But stretch that distance to Mars and the pause becomes profound. Depending on where the planets are in their orbits, the delay between sending a signal and getting a response from Mars can range from 5 minutes to over 20. That means a round-trip conversation can take nearly an hour. Hello. 5 to 20 minutes later. Hi there. Not exactly great for casual chats. And so when we send rovers to Mars, like Curiosity or Perseverance, they're not remote-controlled in real time. We send instructions in packets, and the rover follows them on its own. Then it reports back. The process is careful, scripted, full of patience. There's no joystick, no "oops, let me fix that." Just trust in a machine on another world, following the last set of commands we managed to whisper across the void. And farther still, the Voyager probes, launched in 1977, are now over 20 billion kilometers from Earth. Signals from Voyager 1 take over 22 hours to reach us. A message, and hearing back tomorrow. Minimize the technology's fault. It's not lag or interference, it's just physics. No matter how good your signal is, you can't make light go faster. Sometimes the delay even turns bittersweet. Confiscated NASA lost contact with the Columbia Space Shuttle just minutes before re-entry. The final data, travelling at light speed, arrived seconds after the shuttle itself was already gone. Light delivered the last heartbeat just after the story had already ended. The filer's sparse world and final diveries. The resilitive travelling with UC is speaking to you from the past. The light from Sirius left its star about 8 years ago. The light from Betelgeuse, around 640 years ago. If you're looking at a galaxy in a deep field image, you might be seeing it as it was billions of years ago. Blindly the quiet truth. Buckley, the sun, our closest star, is delayed. When you watch it rise, you're not seeing now. You're seeing 8 minutes, seconds ago. If the sun were to vanish, poof, it would still shine in our sky for those 8 extra minutes. Light, for all its speed, is not instant. It's a messenger with limits, a patient traveller. It moves at the only speed the universe allows, and no faster. So when you speak into the dark and wait for a reply, whether to a rover, a star, or a distant probe, remember, the silence isn't emptiness. It's just time catching up. Let's say you open a photo album and find an old picture of someone you love, taken long before you met. They're smiling, waving, frozen in time. That photo doesn't tell you what they're doing now, but it tells you who they were once. That's exactly what a telescope does. It doesn't just magnify, it reaches into the past, one photon at a time. Every time you look through a telescope, whether it's a backyard one or the James Webb in deep space, you're not just seeing distance, you're seeing delay. Because light takes time to travel, every image is an echo, a snapshot of something that may already have changed or faded or vanished. And the farther you look, the deeper into time you go. The moon, just over a second old. Shameful, 8 minutes. The closest star system, Alpha Centauri, more than 4 years. Parliamentary galaxies, we see them as they were millions or billions of years ago. This is not just poetic, it's physical. Light is the universe's delivery system for information. It carries clues in its colour and its intensity, in the way it's bent or stretched. When a telescope gathers light, it's gathering stories, not in words but in frequencies. Schizophrene blue star tells us it's young and hot. Windshield galaxy, tail-shifted galaxy tells us it's distant and retreating. Might be one of the very first galaxies that ever existed. Demolished are not passive. They are time machines built to chase ancient light and decode it. Some are tuned to visible light, like our eyes. Others reach for radio waves, X-rays, gamma rays, types of light our bodies can't detect but which reveal things our eyes would miss. Discharged the Hubble Deep Field, for example. Astronomers pointed Hubble at what seemed like a dark, empty patch of sky and left it there for days. When the image was finally revealed, it was teeming with thousands of galaxies, each one a fossil in flight, a window into a chapter of the universe that had long since passed. Minimize the cosmic microwave background, the oldest light we can detect, was once trapped in a fog of particles, waiting for the universe to cool enough for photons to move freely. That light, now stretched into microwaves, tells us what the cosmos looked like over 13 billion years ago. And here's a quiet truth: many of the galaxies we see in deep space no longer exist. Their shapes may have changed, their stars may have gone supernova, their light left before humans ever walked the Earth, and we're only catching it now. When you gaze at the stars, you're not just stargazing, you're time-gazing, backbone, and in that starlight there's a kind of comfort, because the universe never truly hides the past. It leaves it drifting in space, like postcards from long ago, waiting for someone, somewhere to receive them. Even your own eyes are time machines in a way. When you look across a room or at the face of someone dear to you, there's a microscopic delay. Light travels from them to you. Your brain receives it, interprets it, turns it into meaning. It happens fast enough to feel instant, but it's never truly now. There's always a breath of time in between. And telescopes? They're built to breathe in the ancient, not to change it, just to witness it. You flip a light switch. The room brightens. To you, it feels instant. So fast that the cause and effect blur together. One finger tap, and suddenly the dark is gone. But beneath that simple act is something more curious. Because light doesn't actually move instantly. It just moves fast enough that your brain can't tell the difference. Light travels at nearly 300,000 kilometers per second. That means a beam of light can circle Earth more than 7 times in a single second. From the light switch on your wall to the bulb above your head, that distance is covered in fractions of a microsecond, a span of time so short your nervous system doesn't even notice. Your brain takes longer to register that the light is on than the light itself takes to travel. Shimmer isn't just a footnote. It's a reminder that perception and physics aren't the same thing. Another example. When you watch a storm from a distance, you often see lightning before you hear thunder. That's because light travels faster than sound. You've probably counted the seconds between flash and boom, estimating how far away the strike was.
But the light didn't arrive instantly. It just felt like it did. Because even from miles away, it still gets to you in less than a blink. Blackmail goes for watching someone wave from across a field. There's a delay, small, imperceptible, but the wave you see happened just a split second earlier. Even looking in a mirror isn't real time. Light has to bounce off your face, hit the mirror, and travel back to your eyes. Again, it's nearly instant, but it's not perfect. You're seeing yourself a tiny fraction of a second ago, an echo of a moment already gone. And your brain? It's not just a camera, it's a storyteller. It smooths the data it receives. It fills gaps. It ignores delays too small to matter for survival. Your eyes and brain work together to create a version of reality that's continuous, cohesive, and fast enough to feel real. But underneath, the delays are always there. A nerve impulse takes time to travel. A friendship's, a neuron, takes time to fire. In a way, you're always living a tiny bit behind the present, watching the world not exactly as it is, but as it just was. Evolution didn't build us to be physicists, it built us to function, and for that, near instant is plenty. Blessed, because in every instant, there's a whole choreography unfolding. Light zipping across the room, eyes catching photons, brains decoding patterns, meaning blooming in the space between signal and self. Like catching someone's glance.
Imagine you're standing on a quiet hill at night. You shout into the darkness, not to be heard but to wait. Seconds pass, then faintly an echo returns from some distant cliff. A reply not in words but in presence, not instant but faithful. This is how science listens to light. Not as a flash, trembling but as a delayed arrival, a traveller who never hurries but never strays. When scientists work with light, they're often not chasing brightness or colour, they're chasing timing. Tiny imperceptible delays, the kind of shifts that hide in nanoseconds, or picoseconds, or intervals so short they'd be lost in the blink of a blink. To detect these delays, we've built instruments of remarkable patience. Relocated the LIGO observatories, for example, sit in long vacuum-sealed tunnels, waiting for laser light to change by a fraction of a wavelength. If space-time itself stretches or compresses, just a whisper, just once, LIGO can tell. But only because it waits, because it holds its breath, watching light move back and forth, again and again, until something finally shifts. These are not experiments for the impatient. Sometimes researchers collect photons one by one over weeks, building a single image from pinpricks of ancient light. Telescopes stare at empty patches of sky for days, just to reveal galaxies whose light began its journey when the Earth was still molten rock. Even on Earth, science listens for delay. Flirting in laboratories, time-of-flight measurements track how long it takes for a photon to move from one place to another. They use lasers, mirrors, detectors, all choreographed to capture that fleeting moment when light finishes its run. Position when measuring tiny variations in temperature or motion, researchers rely on light's consistency. If it takes just a little longer to return, they know something has changed. Works without trust in light's rhythm, makes measurement possible, not just our tools, but our confidence that light will always move at the same pace, that every delay tells us something real, that a pause is not noise, it's data. In a way, science is an act of quiet attention, coveting to sit with slowness, to hear what's not immediately obvious, to know that answers sometimes take time, and that this time is baked into the fabric of space itself. Even now, signals from space probes, some launched decades ago, are still being received. Faint pulses, fainter still, each one arriving late but still meaningful. And the instruments listening? They're not disappointed. They're ready. Poetic about that, isn't there? Of rush and speed, our greatest truths are often found by waiting, by measuring delays, by trusting that even the smallest pause is filled with meaning, that it does take its time. And that's the only way we ever learned what time really is. Let's start, as so many quiet wanderings do, with a dream. You're in a spaceship, sleek, silent and built for speed. Ahead lies a distant star, light years away. You push forward past planets, past the edge of the solar system, and then faster, faster still, until space itself bends into streaks and stars blur like rain on glass. You've gone faster than light, imprisoned in stories.
Science fiction is full of faster-than-light travel, warp drives, jump gates, wormholes, hyperspace corridors, and why not? The distances between stars are staggering. Even our fastest spacecraft would take tens of thousands of years to reach the nearest one. So we imagine ways to bend the rules. We write ships that leap in an instant, characters who arrive before they leave, whole civilizations built on a universe where the speed limit doesn't apply. But physics is quieter and stricter. Its theory of special relativity, the speed of light isn't just fast, it's a kind of cosmic boundary. As you accelerate toward it, strange things begin to happen. Time, from your perspective, slows down. Clocks tick more gently. Distances ahead of you seem to contract. But you never quite reach the limit. The closer you get, the more energy it takes, not in some simple, linear way, but exponentially. Getting a spaceship to 90% the speed of light is possible with enough technology and power, but 99% takes vastly more. And 99.9999%? The energy cost approaches infinity. Bathrooms, and that's the catch. Hubble light, you would need infinite energy. And in this universe, infinite anything is a quiet way of saying impossible. Even more, as you accelerate, your mass effectively increases. Not in the sense that your body gets heavier on a scale, but in how it resists further acceleration. It becomes harder and harder to push, as if space itself is holding you back. The light speed limit isn't a wall you crash into. Falsely, it's a slope that steepens forever. This is why nothing with mass can reach or exceed light speed, not because we haven't figured it out yet, but because the structure of reality doesn't permit it. But this doesn't mean fast travel is hopeless. Relativity gives us a loophole, one that's not about breaking the limit, but working within it. If you travel near the speed of light, time slows down for you. From your perspective, the journey is brief, even if, from Earth's point of view, centuries pass. This is the essence of the twin paradox. One twin stays home, the other boards a spaceship, travels near light speed, and returns. The spacefaring twin is younger, having aged more slowly. You can cheat time. You can experience the journey in days or years, while light years pass in the outside universe. But going faster than light? As another matter. That opens doors that shouldn't open, doors to paradox, broken causality, and a universe where effect can precede cause. Still, the dream lingers. It's comforting, isn't it? The idea that you could leave tonight and wake up beside another star. That distance isn't a barrier, but a veil we can part. Even knowing the laws, we still imagine. Imagination is faster than light. Blackmail to the end of the universe and back before you blink. But physics moves at light speed. Faster. Let's step for a moment into a space where equations are more generous than nature. In the math of special relativity, there's nothing that outright forbids faster than light particles, at least not on paper. You can rearrange the formulas, flip a few signs, you end up with something strange. A particle that always moves faster than light, never slower. A particle that in theory could never be caught. Financially gave these imagined travellers a name, tachyons. The word comes from the Greek tachy, meaning swift, and they are, in every possible way, slippery. Tachyons wouldn't need to accelerate past light speed. They would start there, born beyond the boundary. They'd be the opposite of everything we know. Instead of needing infinite energy to reach light speed, tachyons would need infinite energy to slow down to it. In math it works. It's not made of chalk and symbols. Let's gently walk through why tachyons might not belong here. The first problem is imaginary mass. When you plug tachyons into Einstein's equations, their mass becomes the square root of a negative number, something real physics doesn't know how to handle. It's not just difficult, it's unphysical. Set that concern aside and ask, what would happen if something really could go faster than light? It wouldn't just get somewhere quickly, it would break how we understand time. Because when you allow faster than light motion, it becomes possible, under certain reference frames, for an effect to happen before its cause. You could send a message to someone, and they might receive it before you send it. This is not just confusing, it's a causality paradox. And physics, as it turns out, is quite protective of causality. It's one of the few things that seems to hold across every experiment, every observation. The future follows the past, not the other way round. So tachyons ignore this rule. They could let you build circuits of paradox, feedback loops that unravel logic itself. You could, in theory, use a tachyon signal to warn yourself not to send it. And if you listened, the signal would never be sent. But if it wasn't sent, How did you receive the warning? This kind of puzzle, called a causal loop, is a hallmark of impossible physics. It's where our intuition breaks down, and more importantly, it's where reality tends to push back. To date, no evidence for tachyons has ever been found, not in particle accelerators, not in cosmic rays, not in subtle deviations from theory. They remain hypothetical, a whisper of what might be if the universe were just slightly different. But the universe we inhabit seems to say, no. Congest angrily, breached, just firmly. Doesn't mean imagining them is useless. The idea of tachyons helps us test the edges of theory, to ask, what would break if this were true? What must remain in place for the world to hold together? Priesthood, and often by studying what doesn't exist, we learn more about what does. So, yes, tachyons make beautiful math. Kissed each other through space-time diagrams with impossible grace. But in the quiet universe we observe, they've left no footprints. Maybe they never were. They're racing forever ahead, never touching anything, never speaking. Just mathematical ghosts, flickering beyond the limit, where the light cannot follow. Let's begin with something simple. You pour a cup of tea, then take a sip. First the action, then the result. First cause, then effect. It seems obvious, so ordinary that we barely notice it. One thing leads to another. This order forms the quiet scaffolding of reality. It's not just about physics, it's about stories, about memory, about sanity. But what if that order could break? What if something could happen before the thing that caused it? Propensity, that's the slippery slope we step onto when we imagine things moving faster than light. In Einstein's special relativity, time and space aren't fixed backdrops. They bend and shift depending on your motion. If you're moving very fast, say close to the speed of light, your view of time is tilted compared to someone standing still. Normally, that tilt doesn't cause problems. Everyone still agrees on what happened, even if they disagree about when it happened. But if something could travel faster than light, that's when the trouble begins. Because faster than light travel means that in some frames of reference, events can flip. What looks like a signal being sent from A to B in one person's perspective might look like the signal arriving before it was sent to someone else. The line between before and after begins to blur. Imagine this. You send a message to your friend across the galaxy, but in their frame of reference they receive your message before you sent it. Then they reply, still faster than light, and in your frame you receive their reply before you ever sent the original message. Congratulations, you've just created a causal paradox. Xiaomi isn't just mind-bending, it's logic-breaking. Because now you could send a message to tell yourself not to send a message. If you follow your own advice, the message never goes out. But if it never went out, how did you receive the warning? Confiscated the grandfather paradox, dressed in photons and equations, a loop where cause and effect chase each other in circles, each erasing the other's reason to exist. It's like reading a book that deletes the chapter you're currently reading. Physics, as far as we know, doesn't allow this. That's why the speed of light is so much more than just a speed. It's a boundary for causality, a rulebook for reality. It ensures that events have a consistent order, that actions precede reactions, that stories have beginnings before endings. Some theories propose mechanisms to protect causality. They suggest that even if faster than light travel were somehow possible, nature would find a way to block paradoxes. These are called chronology protection conjectures, ideas whispered from quantum gravity and curved space-time. But so far, all evidence says we live in a universe where faster-than-light communication, motion, or influence is forbidden. Not because it's difficult, because it's dangerous to meaning. And without meaning, we have no physics, no memories, no of time. Order. Tea. Before sip. Question. Before answer.
cause before effect. Because anything else, would be a universe we couldn't understand. Imagine folding a piece of paper. Two distant points, once separated by the full width of the sheet, now touch, press quietly together. What once required a long journey across the surface can now be crossed in an instant through the fold. The gentle metaphor behind a wormhole. Of general relativity, space and time are not rigid. They bend, stretch, ripple. A wormhole is one of the most exotic shapes that this bending can take. A tunnel through space-time. Not a shortcut in space alone, but in space-time itself. They're allowed. Einstein's equations permit them. Positioned. The concept first emerged in 1935, when Einstein and physicist Nathan Rosen explored solutions that became known as Einstein-Rosen bridges, what we now romantically call wormholes. These theoretical tunnels could, in principle, connect two distant regions of space. You enter one end, step across the bridge, and emerge somewhere else, perhaps light years away, perhaps even in another time. Freezes, as always, the universe is more careful than it seems. Wormholes, as the math describes them, are unstable. If one were to form, even by accident, it would likely collapse before anything could travel through it, like a soap bubble trying to support a brick. Turbulence a wormhole open, you'd need something peculiar. Exotic matter. Matter with negative energy density, the kind that would resist gravity instead of submitting to it. We've never seen such stuff in nature, though quantum physics hints it might exist in fleeting forms, like the vacuum fluctuations of empty space. Believe that if exotic matter could be stabilized and shaped, it might hold a wormhole open. The tunnel would no longer collapse. It could remain open long enough for something, maybe even someone, to pass through. Flooring, then, problems arise. Because if a wormhole connects two regions of space, and one mouth is moved, accelerated, or aged differently, you might create not just a shortcut in space, but a loop in time. You could, in theory, create a time machine. And with time machines come paradoxes. Deposited, you might be able to send information or even travelers into the past, and as we saw before, this opens the door to causality violations, messages arriving before they were sent, effects preceding causes. Squeezed, again, physics starts to push back. Makeshift suggests that quantum effects would destabilize any such wormhole the moment it could violate causality. This is part of what's known as chronology protection, a kind of cosmic immune system that keeps time from unraveling. Till the idea lingers, gently, quietly. Wormholes are not forbidden by theory. They sit at the edge of what's possible, neither confirmed nor conclusively ruled out. They occupy a space between what the universe says is allowed and what the universe is willing to allow. And maybe, just maybe, that's enough for wonder. In fiction, wormholes let us charging, traverse galaxies in moments. In physics, they let us imagine what might exist, if the laws were just slightly more generous. They remind us that space-time is not a grid, but a fabric, and that in the folds of that fabric secrets may lie, waiting to open. Or maybe not. Let's begin with a pair of gloves. You place one in a box and mail it to a friend across the world. You keep the other with you. When they open their box and see a right glove, they instantly know you have the left. It's not magic, it's correlation. You agreed on the pair from the start. Now let's turn up the strangeness. In the quantum world, particles can become entangled, their properties mysteriously linked no matter how far apart they drift. Not like gloves where the state is predetermined, but like dice that somehow always land with matching numbers, even when rolled on opposite sides of the universe. Einstein didn't like this. He called it spooky action at a distance, because it seemed to suggest that one particle could affect the other instantly, faster than light could travel. Important part, entanglement isn't communication. When you measure one entangled particle, its state appears, and when you measure the other, you get a matching or opposite result depending on how they were linked. But you can't choose what outcome you'll get, you can't control it, and you certainly can't use it to send a message faster than light. Propane. It's like opening your glove box and finding a random glove. It's only when your friend opens theirs that the pattern makes sense. Until then, all outcomes are possible. This randomness, this lack of control,
is what keeps entanglement from breaking the cosmic speed limit. It's strange, it's unsettling, but it respects relativity. In fact, this has been tested over and over. Experiments called Bell tests have confirmed that entanglement is real and that quantum particles do influence each other in ways that can't be explained by local hidden variables. But they still don't send information faster than light. Imagine two people flipping coins on opposite ends of the planet. Every time one flips heads, the other gets tails. It seems impossible, and it is, unless the coins were entangled. Blackmail is still random. You can't flip a head on purpose to make the other person get tails. There's no message, no Morse code, no control. Congressional. Some researchers have even tried to push the test farther, setting up entangled particles so far apart that light itself wouldn't have time to travel between them before the measurement was made. And still, the spooky match persists. The universe, it seems, doesn't care about distance when it comes to quantum entanglement. Abolish, and yet. Blackmail, it doesn't cheat. It doesn't whisper secrets across space. Reveals that space and connection are not quite what we thought. There may be a deeper framework beneath space-time, one we don't yet fully understand, a place where here and there are not as separate as they seem. But until we can grasp that deeper level, we're left with what we can observe. Fiberglass entanglement is entirely consistent with the speed of light being the schism.
Limit. Timing, it feels. So if someone tells you quantum physics lets us communicate faster than light, you can smile, shake your head gently and say, confiscated, and that's weirder than that, but not faster.
Picture yourself standing at the edge of an ocean. An endless, soft,
The line where sea meets sky. That distant place, the horizon, feels like a boundary. Not a wall, not a barrier, but a limit of what you can see. And if you wait long enough, perhaps a ship will emerge from it, perhaps not. The speed of light draws a horizon too, but instead of oceans it works with space and time. And unlike that watery edge, some horizons, once crossed, never return anything. Let's begin with one of the most mysterious, the event horizon of a black hole. This is the boundary from which not even light can escape. If you cross it, there's no coming back. Not because you're crushed, not yet, but because space and time inside are so warped that every possible path leads you deeper in. Inside, it's as if time freezes at the horizon. A person falling into a black hole would appear to slow down, dim and stretch. Forever, their final moments painted onto the horizon like a cosmic shadow. That's what a speed limit does when taken to its ultimate conclusion. The event horizon is where light hits its limit, not because it stops, but because the geometry of space has turned in on itself. Now widen the view. The universe itself has a horizon, the cosmic light horizon. This is the farthest distance from which light has had time to reach us since the Big Bang. Anything beyond that edge lies forever out of reach. Not just too far, but too far away, too fast. Space is expanding. Galaxies are riding that expansion. And beyond a certain point, they are receding faster than light can catch up. Prohibited doesn't break the rules. They aren't moving through space faster than light. Instead, space itself is stretching, carrying them with it. You draw them close together, then blow up the balloon. The dots move farther apart, not because they're speeding across the surface, but because the surface is expanding beneath them. Like the balloon, the universe has regions we will never see because their light will never reach us. Not now, not ever. Not because they're hidden, but because the rules won't allow it. The loons of light draws a quiet line across the cosmos, blackmails far and no farther. And yet, it doesn't feel cruel. It doesn't even feel final. These horizons don't imprison us, they shape us. The Beck observable universe is a bubble of experience, a memory sphere, a soft envelope of what we can know. And it grows, very slowly, as light from distant events finally arrives. Dismissing contains mysteries we can never chase. Galaxies already lost to expansion, stars whose light will never come. Not because they're unwilling, but because we started too late. And so, the speed of light becomes a kind of silence at the edge of things, a silence that marks the difference between what is here and what is forever beyond. The horizon isn't a fence, it's a whisper, telling us where we are and where the light has not yet been. We often think of limits as disappointments. They are the edges we bump against, the fences we can't climb, the boundaries that say, no farther. And in the case of the speed of light, the universe has drawn a particularly firm line, one we cannot cross, no matter how clever our engines or how advanced our math. But let's take a slower look. Because sometimes limits don't imprison us, they give us shape. Because music, without a rhythm, a key, a structure, there's no melody, just noise. Or think of language, without grammar, words fall apart. Even games need rules to be meaningful. The thrill of strategy, of play, comes from working within the constraints. And so it is with the cosmos. The speed of light isn't a failure of our ambition. It's the framework in which the universe becomes knowable. It tells us which events can influence others. It tells us which things are connected and which are too far to touch. It's the reason stars shine in a predictable way, why galaxies form orderly spirals, why time flows in one direction instead of looping into nonsense. It protects causality, the simple faith that if you boil water, the kettle will whistle afterward, that if you speak, your words will reach someone later, not sooner. It lets stories have beginnings and endings. It allows reality to unfold gently, step by step, without unraveling. In the absence of limits, chaos blooms. Defiance could jump ahead of time. If particles could zigzag through the past and future at will, the universe would be unworkable. Not magical, just broken. The quiet clockwork we observe would dissolve into contradiction. But that doesn't mean the universe is dull. Fog the rules still allow for wonder. Black holes, supernovae, entanglement, expansion, quantum leaps, the dance of light and gravity. There's still mystery, plenty of it, but it's mystery inside a container, the kind that lets us discover instead of drift. Fall back, and here's the comforting part. This speed, we can work with it, build with it, trust it. It's why we can send signals across space, why our GPS works, why telescopes can show us the early universe. Light gives us limits, but those limits are what make communication, navigation, and understanding possible. And in a deeper sense, they give us a place. Fiberglass, when there's a horizon, something you can't cross, you suddenly realize what lies inside that horizon matters more. It's a soft invitation to pay attention to the present, to the here, to the now, to the patch of cosmos where light can still reach you. You don't need to outrun the speed of light to feel awe. Not a stop sign, but a shape. Not a no, but a kind of yes, softly whispered. Yes, to connection that takes time. Of what matters. It's the outline of everything that does. You've heard it 100 times by now. Light is the fastest thing there is. But maybe, after everything we've explored tonight, you've come to see it a little differently. Not as speed, but as tempo. Not as a sprint, but a steady rhythm that the universe hums to, quietly and faithfully. The speed of light doesn't rush. It doesn't blur. It gives space its meaning. It lets time unfold at a pace that we can live inside. It doesn't shout. It whispers. It's everywhere. It's in the 8 minutes between the sun's surface and your morning coffee. Alphabetical. It's in the 22 hours it takes for a signal from Voyager 1 to arrive back at Earth. Still travelling after all these years. Still humming through space like an old lullaby that hasn't forgotten its final verse. Kang, it's in the way galaxies drift apart at the edge of visibility, so far that their light will never reach us, but close enough that their once bright past still flickers through our telescopes. Light does not compete, stimulate, moves. Always forward, always patient. If it were any slower, we'd be blind to the stars. If it were faster, we'd never see the past. We'd miss the poetry in delay, the quiet stretch between cause and effect. We'd miss the grace in waiting, the gentle unfolding of things. It's a strange comfort, isn't it? Knowing that everything you see is a little old. That the world arrives to you not all at once but with soft lag, like a memory that hasn't quite settled. The stars don't rush their stories.
They tell them as light allows. And so, even your thoughts tonight have ridden on that same tempo. Defiance, from Einstein's imaginary journey on a beam of light. Twin astronauts aging at different speeds. Tons echoing from the first seconds of the universe. Confiscated by a cosmic metronome, ticking not with urgency, but with continuity. You don't have to move faster than light to feel wonder, have to understand every equation to feel its beauty. Proportional, have to pause, to notice, to feel that what is arriving to you now has travelled far, and long, and honestly. And now, as the night deepens and the world quiets around you, you can let that same tempo carry you. No rush, just the slow rhythm of distance closing, profitability breath, light arriving, softly, like thoughts settling after a long day.
In a world that so often demands speed, there's something quietly radical about waiting. Tonight, you've wandered through a universe that moves at the pace of light. Not rushed, not delayed, just exactly as it must. You felt the softness in its boundaries, the stretch of time between stars, the hush of signals whispered from deep space. This is not a universe of shortcuts, patience. And perhaps you've noticed, patience isn't absence. It isn't empty. It's filled with potential, with meaning slowly making its way to you, with the subtle weight of things arriving not when you want them, but when they're ready. Waged. When you look at the stars, you're seeing a kind of memory. Position. Not because the stars are gone, though some may be, but because their light is still travelling, still bringing you their stories even now, even here, from across years, centuries, lifetimes. And light, slow as it might feel on a cosmic scale, never stops trying. That's what science does too. It waits. It listens. It trusts that with enough time and enough stillness, answers will come, not all at once, but with rhythm, with grace. Our life has its own light speed rhythm. You wish would come faster. Answers that haven't yet arrived. Dreams still working their way toward you. His quiet night, you are still receiving. A breath delayed is still a breath. Position late is still a gift. And a universe with limits is still limitless in what it can mean. You are not behind. You are not too slow. You are moving exactly at the speed of light's embrace. Fiberglass. So as you settle in, eyes softening, thoughts unwinding, know that this moment is not empty. It is simply spacious. There is time for you here, time to be, to drift, to rest. Let go of chasing what's just ahead. The universe isn't in a hurry, and tonight neither are you. Let yourself float, like starlight crossing distance, like silence crossing thought. Crimson, when you sleep, sleep like a photon, flooring, unrushed, frayed, and always headed home.